Hello everybody. For those who haven't met me yet, I'm Răzvan, and I'll be presenting you how to use OpenSIPS as an edge proxy. First of all, a few words about me. I've been working with OpenSIPS for 5 years. I'm one of the core developers. I've implemented some features like ACC CDRs, automatic CDRs, and event interface. And lately, I've implemented the WebSocket protocol. We'll discuss about the WebSocket protocol later. So let's see what's the presentation about. First of all, we'll find out why you need an edge proxy. Probably not all of you are using it. Probably some of you don't really know what it should do. Next, we'll see how you can use OpenSIPS as an edge proxy and why you would use OpenSIPS as an edge proxy. And finally, we'll have a technical workshop where we'll see a few tricks of configuring OpenSIPS to work as an edge proxy to multiplex different protocols and so on. So let's see, what is an edge proxy? Basically, context topology consists of several core engines. So these are very sensitive, they are very smart. They do routing, they do accounting, there might be multiple instances that communicate between them. The problem with this is that they are smart, and if they are smart, they are very sensitive in terms of security, in terms of crashes, redundancy, and so on. That's why you would like to offload somehow some of the capabilities of the core engines to the other components. That's where edge proxies stand by. So basically, this diagram shows a core engine, a very smart core engine that has in front of it a few edge proxies that speak to the clients. So the clients do not speak directly to the core engine, but rather to the edge proxy. The core engine is inside the private network, so clients can go directly to the core engine, but here we have the public network. That's one possibility. Another possibility is to have multiple engines and use the edge proxy as somehow a load balancer. So having the edge proxies here, the clients in front of it, you can easily dispatch the request to one less loaded core engine. So basically the idea is the same. However, here we also have load balancer capabilities. The same, the core engines should be in a private network and should not be accessible from the outside, from the public network. What does an edge proxy? Well, first it needs to authenticate clients. It needs to make sure that everybody who reaches the core component is allowed to do it and to authorize it and so on. Another thing that has to be done on the edge side is filter the traffic. There might be non-SIP packets that should not go into the core network because you don't know we can do anything with them. They can detect attacks, and they can leave out or filter malformed packets because these kind of packets don't really need to go into our core network, right? We want the core network to be as protected as possible and as stable as possible. Different stuff like normalizing the traffic. For example, having big SIP packets it's not worth having big SIP packets over our entire network if only the end client, the end user, uses them. So we can add some headers or remove them. At the edge side, we can have different protocol support. For example, what we can do is on our edge proxy offer different protocols like UDP, TCP, TLS, WebSocket, but our core engine can only speak UDP, and therefore we have to make somehow a protocol translation. And a very important thing that has to be taken into account when using an edge proxy, it has to be very easy to scale it. Because if you add more customers, then you can easily add an edge proxy. And also, probably, if the core network doesn't handle the traffic, you can easily add multiple cores to support your customers. So it's very important to be easy to scale. Also, it can work as a load balancer to balance the traffic across multiple core engines, and also can offer or should offer topology hiding depending on your customers. You might want to hide the core components from your customers. And we'll see this in the workshop today. How can OpenSIPS do that? Well, probably most of you already know that OpenSIPS does have digest and IP-based authentication. Can easily detect non-SIP messages and discard them even from the core, so they don't even reach the script. Also, it does have a 3261 RFC compliant SIP validation method that you can detect the malformed packages even from the start, even from the beginning of the script. Can detect attacks using the pipe module, and starting with 2.1 we have the fraud detection module that can detect attacks based on calling patterns. Can normalize network protocol. Probably most of you know that OpenSIPS supports different transport protocol like UDP, SCTP, TCP, TLS, WebSocket. And probably the customers want to use any of them, so you can, your platform doesn't allow you to impose your customers what they should use. An edge proxy would be wonderful if an edge proxy could normalize everything to UDP, normalize everything to UDP and pass it along to the core engines. And when the requests get back, they translate it to the desired protocol. Moreover, an edge proxy should shape the SIP traffic, should add the received port, should normalize the contact header with the proper IP and proper port, should, well, yesterday Bogdan asked you whether you had problems with big SIP packets. What's the problem with big SIP packets? Is that they get fragmented and they're somehow lost. Well, in 2.1 we have actually two solutions for this. One of them is to use the short names for the SIP headers. For example, use the M, the I, C, L instead of call ID, instead of content length, instead of contact header. So instead of having 5-6 letter headers, we only use one letter. This means that our SIP packets get smaller with like 10 or 20 or 30 characters. Moreover, we implemented the compression module. The compression module allows you to compress the body and the headers in such a way that using gzip and allows you to compress these headers and pass them along into your core network. Of course, when they get out of the core network, they have to be decompressed, because otherwise nobody will be able to read them. And as I said, you might want to add or remove different headers. You should also handle media on the border. Why? Because it's very important that media is very close to your customers, and you don't really want to pass it along in your core network. So you shouldn't pass it to your core network. You should keep it as far as possible for the core network, because you would like to scale it. You can easily scale an edge proxy, but it's harder to scale a core. Our solution for OpenSIPS, even though we have been using RTP proxy for a couple of times and media proxy, this time I'll be showing you RTP engine. Probably you know why, because I'll also have a presentation about WebSocket, and well, when you use WebSocket, you want somebody to handle SRTP. RTP proxy doesn't handle SRTP, that's why we had to look in a different direction. RTP engine offers ICE support, which I'm not sure whether you know, but it's mandatory in WebSocket. It offers SRTP support. It offers DTLS to actually handles both DTLS and SDS protocols, and it's also able to bridge RTP and SRTP. Basically, this means that you can customers of yours that does not support ICE, does not support SRTP, can talk to a client that does. So you can discuss between UDP and WebSocket. Also, OpenSIPS can be used as a load balancer. So being an edge proxy should also be able to load balance between core for redundancy and for efficiency. There are a couple of modules that can do this. As far probably you already know them. Is the dial plan module, load balancer, dispatcher, dynamic router. We can also do static dispatching and so on. A very necessary thing when having an edge proxy and a very complex network is that your clients or your customers should not be aware of your topology, because if they are aware, then you are somehow vulnerable. And that's why you usually use topology hiding. How many of you know what topology hiding is used for and uses it? So, okay, a couple of you. Let me tell you where topology hiding is useful. So this is our architecture. We have the core engine and a few edge proxies. Imagine that this client wants to discuss with this client. According to the record route protocol, the client, when the client sends the invite to the edge proxy, when the edge proxy sends it further to the core engine, it adds a record route. This means that the SIP package contains this IP and this IP. Next, when the core engine goes further to this edge proxy, it also adds two headers, this one and this one. So the SIP packet will contain the identity of both this server and this server. Next, this server also adds the IP of this interface and this interface further to the client, and that means that the SIP packet. This means that the client will see the entire path, starting from this client to this client. When the 200 OK goes back, this client will see the entire path, starting from this client to this client, using the record route headers and the contact headers. imagine that this is not very pleasant, and it's kind of a security issue, and as well as a sensitive problem in case you don't want this client to be aware that you are discussing with this client, right? This means that you'll somehow want to hide your entire platform so that your client only sees a big OpenSIPS without knowing the client. So basically, the topology hiding ensures you that the client only sees you. Abstracts the entire network behind a single entity, so that you'll be a single UAC in dialogue with the client. Similarly, this client will only see you. So basically, the entire platform is just a single node that will act as a more or less back-to-back user agent. Okay, everything clear? If so, let's go to the workshop. The workshop today uses this topology. So basically, I have set up the OpenSIPS virtual machine with a single edge proxy and 2 core engines. Since we'll be talking about the core engine today, these core engines will be doing some very, very complex stuff, like when it receives a packet, it simply sends it back, so watch out. Okay, let's see. Okay, so here I have a virtual machine, and these consoles are attached to those to that virtual machine, where I have 3 instances of OpenSIPS. It's the OpenSIPS Edge, OpenSIPS Core 1, and OpenSIPS Core 2. The Edge proxy has configured the dispatcher model to balance between the 2 core servers in a round robin model. So here are my the two core servers that I'll be using for this demo. Here I have a SIP-B module that registers for the Edge proxy. So in this case, the Edge proxy will also act as a registrar, but it's not necessarily mandatory. So let's see how many clients I have registered for this on this Edge proxy. I have exactly 1, and probably it's this client. Okay. So now I registered a client over UDP. I named it UDP just to make sure that just to notice it easier. So the AOR is UDP at the main. This is the IP of my virtual machine. Now this CP acts as a UAS, user agent server, and it's waiting for calls. So currently, this Edge instance only supports UDP listeners and TCP listeners. In this workshop, I'll be showing you how to add TLS support. So let's say you have a customer that needs TLS support, and you want to integrate the script with TLS. Of course, we will have to edit the OpenSIPS configuration script, which is here. Okay. So in order to add a TLS listener, first of all, we have to add a listener directive similar to this one. As you can see, we have a listener for UDP and TCP, and that's what you saw earlier. And now we also want to add one for TLS. Actually, let me. Okay. The protocol is mandatory in 2.1 and has to be specified in front of the AP. After adding the listener, the new 2.1 implementation has to, in 2.1 you have to explicitly load a module that handles this protocol. So let's see the next to do. In our case, proto-TLS is the module that loads TLS. And of course, when loading a module, you have to specify a couple of parameters. The parameters I specified here is verify cert, whether the server should verify the client's certificate or not. We don't really want to. We don't need that because we don't give certificates to our clients. Everybody can register. Here we don't require certificates from clients, so we can generate the certificates for them. We want to use the TLS, the first version of TLS, and then we have to specify the server certificates. These parameters are mandatory. You have to specify the certificate you are going to present to your clients, the private key used to encrypt the certificate, the certificate authorities list. So what authorities you allow to verify your certificates, and another parameter used by the module to somehow count the number of attempts for a packet. The TLS module tries to read a C packet, and if it doesn't succeed in 8 attempts, it will drop the packet and close the connection because something is wrong. Somebody is trying to hijack the connection. Okay? So that's it. All you have to do is to specify these parameters and, of course, restart OpenSIPS. After the OpenSIPS restarts, we'll see that another actually, we can see here, but some TLS workers have started. We can see here. So now we have two listeners on TCP. First is 5060, the TCP listener, and 5061, the TLS listener. Next, let's see. We only have a single customer registered, and it's over UDP. Let's try to register a customer over TLS. First of all, I'd like to start a Wireshark capture to see the communication. I'll filter only the SIP, and SSL traffic, or the WebSocket traffic, because that's what we will be seeing in this demo. And I will use the link phone client to register over TLS. I know there are a couple of other clients, but that's what I had installed. Okay. So we can see here that the lymphome registered over TLS. The transport is TLS. Let's see if we see it in our user location table. Here it is. So now we have two clients, UDP and TCP. Here we can see the communication between the TLS client and our server. That's the register. Can you see it? Can you see it? Should I make it bigger? I'm not sure I can. No. So yeah, here is the communication between the two. Having two clients, let's see how they communicate between them. In order to see that, we will start n-grep capture. And let's call from lymphome, let's call the UDP client. So the call is established. As you can notice here, we have in call status. This black screen is the video streaming from the CP. So of course, CP doesn't generate any kind of traffic. That's why we see a blank screen. And here, CP in the CP client, we can see the invite 200 OK SDK. So that's how we used a TCP client to phone a UDP client. Here we will only see the communication between the UDP, because the TLS, of course, is encrypted, and we can only see it in Wireshark. So this is the initial invite that's translated from TCP to UDP. Notice that we don't really see anywhere the transport, the TLS transport. That's because we are using topology hiding on the edge proxy, and in our scenario, one of these clients was using TLS until here, but we only see this communication, and this communication is always over UDP. Since this guy is doing topology hiding, this guy has no idea about this client, whether he's behind TCP or TLS or WebSocket or whatever. So that's where topology hiding is useful, to hide the components of your topology for the entire network. Okay. So this is the invite sent to the core engine, and as I said, the core engine simply forwards it back to the edge proxy. Let's notice something interesting. So the edge proxy, I said the edge proxy was doing topology hiding, right? So this means that the core component can see the details about the clients. A very important thing that I want you to notice is that the call ID of this invite, so the invite from the edge proxy to the core engine, is something, I don't know, SWK. However, when the core component responds, it's something like this. So it's something completely different. It's a completely different call ID. Is a completely different contact. So this way, the edge proxy has no idea, even though it's the same edge proxy, it has no idea that the two legs are the same call. Okay, so that's where that's another thing that where the topology hiding module is very useful. to somehow abstract the entire call, not only the components. And this can be done by hiding the call ID. Going further, the invite is sent over UDP, of course, to our CP, and there's no call ID hiding from the edge proxy to the client. However, the contact is hidden. So you can notice that this contact is different from the contact that was received from the core proxy. Indeed, the IPs are the same because all three instances are on the same virtual machine, but the ports are different. So if you would have had the edge proxy and the core proxies on different machines, you wouldn't have known the IP of the core or the IP of the client. So you wouldn't have known anything about the other entities. So that's a scenario where the topology hiding module is very useful. What we've done until now it was to see that TLS to UDP bridging is possible at the network level. Now we'll be discussing about WebSocket. So WebSocket, I bet most of you know what WebSocket is, right? So WebSocket, it's used to communicate with the browser. So you can use the browser as a SIP client in order to communicate over web. In 2.1, we've implemented the WebSocket protocol, so that this means that we can interconnect different clients, be it over UDP, TCP, TLS, and so on and so forth. So, now I showed you how we can integrate OpenSIPS and enable TLS support. Now I'll show you how we will enable WebSocket support. Again, we open the Edge script. The first steps are the same. We have to declare a listener, load the module that knows how to process WebSocket. Now, a very important thing is that you somehow have to differentiate between TCP TLS clients and WebSocket clients. Why? Because they behave completely different. First of all, they don't use the same media. Let's say they don't use RTP. They use sRTP, and you have to make some sort of translation between RTP and sRTP transcoding. So that's why at the very beginning of the script we flag the messages that are sent over WebSocket. Next, when we are about to relay the message, so we've done the entire routing logic, we have to handle the media. When handling the media, we have to, as I said earlier, we have to take into account whether the clients are behind the regular protocol like TCP, TLS, UDP, or they're behind WebSocket. Why? Because in this case, if the two clients have different protocols, then we have to do some sort of transcoding. So we have four different cases listed here. Whether so we have four combinations, right? If the caller is a WebSocket client or not, and whether the callee is a WebSocket client or not. Based on these checks, we can identify what kind of flags we should pass to the RTP engine application. So here, based on the flags we set earlier, we can determine what kind of flags we have to use. That's for initial invites. For replies, we have the similar logic in the onReply route. So besides the TLS integration, all we have to do is handle the media different, because the two clients might not understand each other. One might use RTP and one SRTP. Okay, so that's all. Having done these changes, we restart again the proxy for the changes to take effect. And then check the interfaces. As you can see, a new interface appeared, listening on port 8080, and this is the interface dedicated for the WebSocket communications. Let's see how many, the link phone registers different contexts, but we only have two ARRs, UDP and TLS. Let's register a WebSocket client. In this demo, I'll use the SIPML. I'm not sure whether you're familiar with it. I'll use the SIPML library to run a WebSocket client. Let me get the. Okay, I'll start simple. Okay. Okay, it's localhost. Just a second. Okay. Okay. Now I've opened the. Oh, actually, it doesn't really matter. The client should have been in the virtual machine. That's why. But it doesn't matter. So now what we have to do is to specify our server. In this case, our server is listening on the WebSocket interface on this IP using this port. And then just log in. So now we've registered a WebSocket client. Let's see in the server. Using the user location show command, we can clearly see that a new customer has been registered. So now we have three different customers, three different clients: a UDP, a TLS, and a WebSocket client registered on our network. A very interesting thing is that check the contact of the TLS user. As you can see, it has a proper host and proper port, as well as the transport TLS that customer. So the APN port of the customer. However, on the WebSocket contact, we will always have an invalid host. Why? Because the WebSocket client can't really know the address that he listens on. So you will never see a proper host here. And even though you will have seen one, it will not be a valid one. So most likely won't be a valid one. However, the transport equals WS is here. So what do we usually do when the contact header is not correct? As you probably know, this is a very important header in SIP routing. So you should have the correct information over there, because that's how you locate the customer. So whenever we have invalid contact headers, we have to fix them. So this is the job. This is a job that the edge proxy has to do, because he's the only one that sees the real identity of the customer. Of course, this is done using the fixed netted contact function. So for WebSocket, you should always use this the fixed netted contact function for invites or sequential requests, and fixed netted register for register messages. Using those functions, you'll see the proper contact, so the proper identity of the customer in the received header. So this is where the WebSocket client is connected. Let's see if our setup works. From the WebSocket client, I'll call the UDP client using video. Okay, so the call was established. We are in call. Here we have an ongoing call. As you can see, the packet was not received yet. So our setup works, right? I wish I would have done a SIP trace. Let's see. Close, and I'll call again. Why? Because I want you to see something. So I called again. I want to see an invite sent from the WebSocket client. Where's the first invite? Here it is. As you can see, the content length of this packet is 834 bytes. This is kind of huge, and it's not the biggest packet I've seen. I've seen thousands of bytes in a single SIP packet. Of course, this is not very pleasant when you're using a very large packet, because the packet might be fragmented and you might lose it. So what we have done in 2.1 was to use, as I said earlier, to use the compression module. What the compression module does is take the entire body and archive it and pass it further to the core network. So this is the third thing we'll be doing. Okay, so what I've done here was a very simple logic for all messages that are coming from something else than are coming from a core engine. Decompress the messages, because if the messages are coming from the core network, it goes to our customer, and our customer can see a compressed body, can use a compressed body. On the other direction, when messages are coming from the customers, we have to compress it. So this way, everything that enters the core network gets compressed, and everything that goes out is decompressed, so that the users can use them and can read them properly. Okay, that was for requests, and that's for replies. Oops. Oh. Okay, so now we restarted the server. Let's make another call and trace the messages. Of course, for both TLS and WebSocket clients, we have to re-register because TCP connections are not persistent over restart. So we registered again the WebSocket client. The UDP client is still up. The call was not closed, but anyway. Okay, let's call again. The call is established, as you can see. Let's see the traces. Let's see how the invite looks like this time. So, as you can see, the invite is a bit different, right? It's not a proper SDP here. It's an encrypted one, and then made base 64 on it. Okay, this is the message received from the WebSocket client and sent further by the edge proxy to the core proxy. This is the message sent back from the core proxy to the edge proxy, and obviously the customer will receive a proper SDP, right? This is a proper SDP. As you can see, it's already fragmented. What I want you to see is that the content length of the request sent to the customer is 1,712. So it's a huge packet, right? It's larger than the MTU. However, what? Okay. However, the compressed SDP had only 840. Oh yeah, that's what we were saying. Yeah. So here over UDP, the message was not compressed and should have been compressed because the content length is very, very small. However, when we send it to the customer, we have to decompress it, so it will be a huge packet. Okay, similar to 200 to the 200 OK message. We receive 615 and pass further 500. So the compression rate is not that good in this scenario. However, it's still something. 200 bytes, around 100 bytes. No, 100. And we don't see the messages sent to the WebSocket client because they are not over UDP, so they might be encrypted. As you can notice, topology hiding is still there, so we haven't break anything. Everything is still in place. I can assure you that actually, let's try. Let's call from LinPhone the WebSocket client. Calling. What? Oh, the WebSocket client is rejecting the call. Well, have no idea why. let's do the other way around. So we call the WebSocket. Here we can UDP. Actually, we've done all the tests, right? Okay, so that's it. In this presentation, we've seen how we can integrate both TLS and WebSocket with OpenSIPS. So as you've seen, there are only a couple of lines that you have to add to your script, and then simply restart it and then and use them properly. One side note is that because WebSocket clients need different clients. Different RTP media handling, so uses different media. We have to use RTP engine so that we can decode the RTP between the two customers. That's it. Thank you for listening. And in conclusion, you've seen, and most of you will be using OpenSIPS as an edge proxy, and you've seen that it can be very flexible and very efficient in a multi-tier, multi-level platform. And I don't know, if you have any questions, let me know. Go ahead.
My question is regarding the compression. In which things do you believe that it should be used compression, and what's the overhead that you have on the probably CPU for encrypt these packets?
Usually compression can be used only when there are components on your path that don't need the SDP. So in this case, this guy doesn't do anything with the SDP, so it's not worth passing the SDP from the edge proxy to the core if he doesn't need it. So that's why we compress it, and then when we send it back, we decompress it. Regarding the performance, there are some penalties, but according to our tests, it is worth doing compression. I mean, it's not very CPU intensive to encrypt or actually to archive 1,000 or 2,000 bytes. So it's peanuts. DB operation is 10 or 100 times more expensive than a simple compression. Sure.
Is there the ability to compress the whole zip packet?
What we can do, and the compression module can do, is compress certain headers. So you can compress both headers and body. However, certain headers are mandatory. For example, the contact, the to URI, the from URI, so the call ID. So this have to be present in the packet, because otherwise the zip compliance would be destroyed.
What about the shortcuts I mentioned before?
What?
The shortcuts, the MI, what was mentioned before. How about you, Bernardo?
I haven't shown you. I didn't show you this. Yeah.
Short names.
Yes. Yeah. You can also use short names for those headers, but they have to be present out there, so you can skip them. They are mandatory. Otherwise, it wouldn't have been. It wouldn't be a zip packet. Other questions? Go ahead.
There is which is the best, the quickest way to make the list of the mandatory headers and to instruct the proxy to compress all the rest. So to leave uncompressed only the mandatory ones and compress all the rest.
Okay. Actually, this is supported because the compression module has three different functions. One is compress, and another one is compact. And the compact function, what it does, it strips, it removes all the non-mandatory headers. So using that function, you can shrink the packet as much as possible. If you really need some headers from the packet, you can specify them in a whitelist parameter. So that function says erase me everything but the mandatory headers, However, I really need, I don't know, RPID or remote part ID header or something like that, so you can preserve it, don't erase it, because the next component needs it. So first you should compact, erase everything you don't really need, and then compress it. And this way you get the best compressor ratio.
Compact also replaces the names and short names?
Yes, it has a few flags that tells you whether you only want to remove the headers or you also want to use the short names. So yeah. Other questions?
Did you make any load test using WebSocket protocol?
Any?
Load test.
Oh, load test. No, not yet, but we have that on our schedule. For both TCP, TLS, and because the entire core has changed and we have to do some load tests to see whether there is a penalty between the two versions or there will go far more better. Any other questions? In this case, thank you very much for listening and for being here. And now I'll leave my colleague Alex to show you how to use the control panel, the OpenSIPS control panel web interface. Thank you very much.